everyone, today we're going to take a look at the role that nitrogen, phosphorus and potassium plays in soils and growing media. Nitrogen, phosphorus, potassium, calcium, magnesium and sulfur are what's known as major or macronutrients. These nutrients are needed by plants in much larger quantities than any other nutrients from a nutritional point of view. For today, we are only focusing on nitrogen, phosphorus and potassium. In addition to the major elements, there are also minor or micronutrients. Here is a list of these elements which I'll focus on in a separate presentation. You may have noticed the letters NPK when buying fertilizer. The N stands for nitrogen, the P stands for phosphorus, and the K stands for potassium. If you see fertilizer with 3 numbers displayed on the bag, this is simply referring to the percent of each nutrient contained within the fertilizer. NPK is the main ingredient for all-purpose fertilizer, as most soils already have ample amounts of calcium, magnesium and sulfur. Nitrogen is a key element in plant growth. Nitrogen is very common in our atmosphere. In fact, 78% of our atmosphere is molecular nitrogen. So how is it relevant in terms of soil and in terms of plants? Nitrogen plays an important role as the major component of chlorophyll, the compound by which plants use sunlight energy to produce sugars from water and carbon dioxide. It is also a major component of amino acids, the building blocks of protein. Without protein, plants wither and die. Nitrogen encourages leafy growth, but if you give a plant too much nitrogen, it'll put all of its energy into growing lush leaves at the expense of flowers and fruit. Hence, it's really important to get the balance right. So how is nitrogen found in soil? There are 3 ways: organic nitrogen compounds, ammonium ions, and nitrate ions. The majority of nitrogen found in soil is usually organic nitrogen compounds. Although this type of nitrogen is not directly available for intake via a plant's root system, it can be converted into a form that is directly available to plants by microorganisms. Additionally, there is a small amount of organic nitrogen that exists in a soluble organic compound, i.e. urea, which can be slightly available to plants. Ammonium ions bind to the soil's negatively charged cation exchange complex, or CEC, and behave much like other cations in the soil. Ammonium ions become available to plants via a process called nitrification, which is a very important part of the nitrogen cycle. Nitrate ions do not bind to the soil solids as they carry negative charges, but exist dissolved in soil water or precipitated as soluble salts under dry conditions. They too form an important part of the nitrogen cycle. Now that we've looked at the types of nitrogen in soil, let's take a look at how nitrogen gets into and out of the soil in the first place. To understand this, let's first take a look at the fascinating nitrogen cycle. The nitrogen cycle is a repeating cycle of processes during which nitrogen moves through both living and non-living things, the atmosphere, soil, water, plants, animals, and bacteria. In order to move through the different parts of the cycle, nitrogen must change forms. In the atmosphere, nitrogen exists as a gas, but in soil it exists as nitrogen oxide and nitrogen dioxide, and when used as a fertilizer can be found in other forms such as ammonia, which can be processed even further into a different fertilizer, ammonium nitrate. There are 5 stages in the nitrogen cycle: fixation or volatilization, mineralization, nitrification, immobilization, and denitrification. Fixation is the first step in the process of making nitrogen usable by plants. Here, bacteria change nitrogen into ammonium. Nitrification is the next step. This is the process by which ammonium gets changed into nitrates by bacteria. Nitrates are what the plants then absorb. Assimilation, this is how the plants get nitrogen. They absorb nitrates from the soil into their roots. Then the nitrogen gets used in amino acids, nucleic acids, and chlorophyll. The next stage is ammonification. This is part of the decaying process. When a plant or animal dies, decomposes, like fungi and bacteria, turn the nitrogen back into ammonium so it can re-enter the nitrogen cycle. Finally, there is denitrification, where extra nitrogen in the soil gets put back out into the air. There are special bacteria that perform this task as well. Phosphorus helps transfer energy from sunlight to plants, stimulates early root growth, and hastens maturity. Insufficient levels of phosphorus in the soil can lead to a decreased crop yield. Phosphorus can be either organic or inorganic. To understand the difference between organic and inorganic phosphorus, it's important to understand the phosphorus cycle in nature. Phosphorus moves in a cycle through rocks, water, soils, sediments, and organisms. Here are the key steps of the phosphorus cycle. Over time, rain and weathering cause rocks to release phosphate ions and other minerals. This inorganic phosphate is then distributed in soils and water. Phosphate is simply a phosphorus atom bonded to 4 oxygen atoms. Plants then take up inorganic phosphate from the soil. The plants may then be consumed by animals. Once in the plant or animal, the phosphate is incorporated into organic molecules such as DNA. When the plant or animal dies, it decays and the organic phosphate is returned to the soil. Within the soil, organic forms of phosphate can be made available to plants by bacteria that break down organic matter to inorganic forms of phosphorus. This process is known as mineralization. Phosphorus in soil can end up in the waterways and oceans. Once there, it can be incorporated into sediments over time, and so the cycle repeats. Most phosphorus is unavailable to plants, as most of it is locked up in sediments and rocks. A lot of the phosphorus in soils is also not available to plants. Bacteria convert plant-available phosphate into organic forms that are then not available to plants. Although other bacteria make phosphate available by mineralization, the contribution is small. Adsorption. Inorganic and therefore available phosphorus can be chemically bound or adsorbed to soil particles, making it unavailable to plants. Desorption is the release of adsorbed phosphorus from its bound state into soil solution. Finally, there's pH. Inorganic phosphorus compounds need to be soluble to be taken up by the plants. This depends on the acidity of the soil. If soils have a pH less than 4 or greater than 8, the phosphorus starts to become tied up with other compounds, making it less available to plants. Let's recap some terms and definitions we've covered so far. Mineralization is the microbial process in which soil microorganisms break down soil organic matter into a soluble, inorganic form that is available to plants. Adsorption is the process whereby molecules adhere to the surface of soil particles. This is different to absorption, which is where molecules are drawn into the soil particles and are literally absorbed. Desorption is the exact opposite of adsorption, whereby the molecules that were adhered to the surface of soil particles are released. Potassium is required by plants in large amounts and is necessary to maintain cell turgor and the plant's water relations, controlling the opening of the stomata. A plant stomata is simply tiny pores present on the surface of leaves which help with the exchange of gases. Potassium therefore increases vigor in plants and helps with disease resistance. It also helps form and move starches, sugars, and oils in plants and can improve the quality of fruit. Just like phosphorus, potassium moves in a cycle with varying factors that either contribute potassium to the soil or remove potassium from the soil. Potassium can be added to the soil in 3 ways: plant residue, mineral fertilizers, and animal manure/biosolids. Before a plant reaches maturity, potassium is recycled back into the soil. Unlike nitrogen and phosphorus, potassium has no organic form in tissue and doesn't require mineralization by microorganisms to become available to plants. Manually applying fertilizers such as potash, sulfate of potash, and potassium nitrate adds to the amount of soluble potassium in the soil. With animal manure/biosolids, these organic materials provide potassium as an accompanying cation. Potassium can be removed from the soil in 3 ways: runoff/erosion, crop harvesting, and leaching. With runoff/erosion, it is where water that doesn't infiltrate the soil and it's lost by surface flow, classed as runoff. Erosion refers to the wearing away of land and soil surface through factors like rain, irrigation, wind, and ice. Both runoff and erosion can result in lost nutrients, including potassium, from the soil. Crops that have more leaf and stems, like alfalfa, remove more potassium than the likes of a grain crop. Leaching. Water can remove soluble nutrients via leaching by transferring the nutrients from one soil zone/layer to another. Leaching happens most often in sandy soils with a low cation exchange capacity, or CEC, and high organic matter soils. Now that we've looked at how potassium can be added or removed from the soil, let's take a look at the third factor, being the potassium componentry in the soil. The 3 components that affect how much potassium is in the soil are mineral potassium, fixed potassium, and exchangeable potassium. Mineral potassium, also known as feldspar, must weather in the soil to become available to plants, a process that can take hundreds of years and add significant amounts of available potassium to the soil. Fixed potassium. When clay soils shrink and swell during dry and wet weather, water-soluble potassium moves or converts into the clay and becomes fixed within clay layers. Exchangeable potassium. This potassium is held on the cation exchange complex, or CEC, and is in constant equilibrium with the soil solution potassium. As plants take up potassium from the soil solution, potassium is released from the CEC. You've heard me talk about the cation exchange capacity, or CEC, a few times now. Put very simply, the CEC is a measure of how well soils can hold nutrients. Finally, let's take a very brief look at the other 3 major or macronutrients: magnesium, calcium, and sulfur. Magnesium is essential for plant growth and development. It plays a vital role in chlorophyll formation and therefore photosynthesis and energy. Calcium is an essential element for holding together the cell walls of plants, plant cell division, as well as assisting in the absorption of other nutrients via a healthy root system. Finally, sulfur is an essential element in forming proteins, enzymes, vitamins, and chlorophyll in plants. When it comes to leguminous plants, such as beans or peas, sulfur plays an important role in nodule development, which plays a major role in nitrogen fixation. I hope you enjoyed this presentation.